Hello everyone, this is Ahona Ghosh, an assistant professor in the Department of Computational Science of Brennware University, Kolkata. Today I will be discussing one of our research papers named as Interactive Game-Based Motor Rehabilitation using Hybrid Sensor Architecture. I will be happy to share with you that this work was published in one of the books of IGI Global Publisher, which was named as Emerging Trends and Applications of Machine Learning. So, what is rehabilitation? Rehabilitation is the action of restoring someone from some sudden abnormalities in their behavior. It can be physical, it can be mental also. Rehabilitation can be divided into three three categories I can say rather. There is physical motor rehabilitation, psychological rehabilitation and cognitive rehabilitation. Motor rehabilitation, also called as physical rehabilitation, is the process to restore someone from physical weakness and disability through some training or therapy. The rapid development in sensor technology has made human action recognition presently an active research area. The use of video games as rehabilitation tool has immensely drawn attention of medical persons in the last decade, and interactive game motivates one to be physically active without or with very less intervention of a trainer. So, we have come up with the idea of designing a game which will help someone to rehabilitate from some physical disability. Now some background studies are there, some literature surveys have been gone through, and in the first reference which we have used here, the authors proposed a predictive mechanism where they have identified the specific people for whom the rehabilitation will be more beneficial from a group of people. And in the second part of their work, they have incorporated an explanatory task where, based on the characteristics of the clients, they have decided who will receive the training. And finally, they have illustrated the use of a machine learning algorithm in both predictive and explanatory tasks to forecast whether a patient needs to undergo a long-term care and identify the risk factors of long-term care placement. Two machine learning approaches, namely support vector machine and k-nearest neighbor, have been compared with already existing rehabilitation assessment potential activities of daily living clinical assessment protocol and shown a better performance. Now, in the second reference, the authors introduced space-time feature to identify complex motion patterns with support vector machine, but it is limited to only some actions, while our proposed work deals with a larger set of actions. In the third reference by Oliver et al., a fuzzy interface system has been developed which collects knowledge of a rehabilitative expert and remotely monitors the exercises performed by the patient. Here, both physical and cognitive rehabilitation have been considered to overcome the limitations of previous works which dealt with only physical rehabilitation. Depending upon the mental condition and stress level of the trainee, the system controls the difficulty level of the exercises, offers help to him or her, and sometimes stops the execution whenever needed. After evaluating the performance of machine learning algorithms over conventional protocols in this field, some authors came to a conclusion that machine learning approaches are less interpretable, but improved clinical protocols can be developed using it always. Analyzed physiological data collected from heart rate and thermal camera sensors during activities of rehabilitation. So the proposed system is capable of predicting the changing pattern of temperature ranges, and by applying image processing algorithm, it evaluated the frequency of breathing. Now, what is Kinect sensor? Kinect sensor tracks position of human body joints situated within a certain range, that is 1.2 meter to 3.5 meter from it, and creates the corresponding skeleton. It consists of mainly 4 parts shown in the figure. The RGB camera is a VGA camera which detects the X and Y coordinates of the body joints, and depth sensor enables the system to detect the corresponding Z coordinates. Multi-array mic isolates the voice of the subject from the noise in the room. The motorized tilt enables us to tilt the sensor head up and down up to plus minus 27 degree according to the need. 20 body joints captured by Xbox 360 Kinect sensor has been shown in the first figure, and the mapping of a human skeleton from a human body is shown in the next figure here. Now the accelerometer, the second device which we have used for data collection here, it is known also as the inertial sensor, which has been manufactured in ESSP laboratory of University of Texas at Dallas. It is made of MEMS sensor containing 9 axes used to capture X, Y, Z axis acceleration, angular velocity and magnetic strength. It works within plus minus 8 gram for acceleration and plus minus 1000 degrees per second for rotation. It has applications in mostly rehabilitative field where higher accuracy is not necessarily required. Human activity recognition, which has applications in various fields like healthcare, some smart environments, some homeland security, can be achieved by it also. Pictorial view is represented in the figure shown here. Now the proposed methodology is divided mainly into 3 parts. The first one is feature extraction, the second one is feature selection, and we have to perform classification after feature selection. So that is the third part. Now from the Kinect sensor, we have extracted 5 features in terms of distance and angle between some body joints. The first one is angle between shoulder right, elbow right and hand right. The second one is angle between elbow right, wrist right and hand right. Third one is distance between spine and shoulder right. Fourth one is distance between spine and hand right, and the fifth one is distance between spine and elbow right. And from the accelerometer, we have extracted 9 number of features, which are mean, variance, median, skewness, root mean square metric, mean absolute deviation of signal, interquartile range, entropy and signal magnitude area. Now for the feature selection part, we have used principal component analysis algorithm, which mainly selects some important features from a large collection of features. Here, if n number of observations are considered having p number of variables, then the number of principal components can be considered as minimum of n minus 1 and p. The pictorial representation is shown here, where first dimension and second dimension are the 2 main components extracted from the feature selection. Now, using classification of support vector machine, we have classified our features into some activities. That is, we have categorized our activities into some pre-mentioned activities. By SVM learning algorithm, the data is sorted into 2 categories. At first, SVM gets trained with a series of data already classified into 2 categories, and after that, the basic support vector machine algorithm works as a non-probabilistic binary linear classifier, which takes a set of inputs and distributes those into 2 classes. Data points are divided based on the gap between them It constructs a model that classifies the given data points into one or the other classes. The gap may or may not be clear between the set of two class data points. The data points can be separable or non-separable based on the gap, as it is shown in the figure. Now the design of our interactive game. At first, the player plays the game. The skeleton is extracted from its body joints, and some features in terms of distance and angle between those body joints are extracted by the Kinect sensor, and speed is extracted by the accelerometer. Not only the speed, also the 9 features we have mentioned previously regarding speed has been extracted from the feature set, and then feature selection is done by PCA, and then classification by SVM, and after the classification, the score calculation based on choice of path and speed of cursor movement based on hand movement is done. The 6 actions: right arm swipe to the left, right arm swipe to the right, right hand draw X, right hand draw circle, right hand draw circle, anti-clockwise draw triangle. These 4 actions have been considered by us for playing the game. The skeletons are shown in the figure here for the corresponding actions. Here the first one action is action 1, the second action is denoted as action 2. That's the things. Now what are the instruction sets? Select the grape, drag the fruit and drop it to the basket. Select the orange colored fruit, drag the fruit and drop it to the basket. Select the fruit which is kept opposite to the banana, drag the fruit and drop it to the basket. Select the fruit which is more than 1 in number, drag the fruit and drop it into the basket. These types of instruction set have been used in there, and the game interface has been shown in this figure, where a user has been asked to drag a fruit into the basket, and for doing this task he has to perform some activities, like he has to swipe his arms to the left, or swipe his arm to the right, or he has to drop the fruit into the basket. Like these types of 6 action set has been mentioned by me also previously. Now, as the total action set, the total feature set cannot be given in the paper, like rather in the PPT also. So a sample feature set for only action 1 and 2 have been given here. Now before PCA it is action 1 and action 2. There are this much of data, this much of feature set before PCA, and after PCA only the important ones have been extracted, and there are only 10 features after PCA. For evaluating the performance, the proposed approach has been compared with the existing ones. At first there is TD-SVM, where 6 actions have been performed under training data of SVM, and for VD-SVM, that means the validation data SVM, the 6 actions has been performed. For TD-SMO means training data of SMO, and validation data of SMO has been shown for all the 6 actions. And for the confusion matrix, there is also TD-SVM, VD-SVM, TD-SMO and VD-SMO. Now kappa statistic. mean absolute rate, root mean squared error, relative absolute error, and root relative squared error. The performance of our proposed approach have been evaluated in terms of 5 performance metrics. This one is kappa statistic, this one is mean absolute error, this one is root mean squared error, this one is relative absolute error, and this one is root relative squared error. The performance parameters chosen for this particular is true positive, false positive, precision, recall, F measure, Matthews correlation coefficient, region of convergence, and precision recall curve. From the graph we have designed after the evaluation, it is clear that our proposed approach is well suited for its own domain. Now the justification about obtained performances. For the proposed chapter, we have obtained values for 8 performance meter. The SVM has been taken as the classifier. Here the data that is taken from 192 observations, explanation of this will be given. It is used for training as well as testing. From these 192 observations, randomly one is selected for testing, and with the remaining 191 observation, training is done. If that one instance is correctly classified, then your accuracy score becomes 100, otherwise 0. This arbitrarily selection of one observation is done 500 times. Then the average is calculated, which becomes the overall accuracy of training data of SVM. As the features are linearly separable, thus 100% accuracy is obtained. This same procedure is again carried out in the next table, but the classifier chosen here is SMO. As this classifier is weaker than SVM in respect of correctly classifying SVM, so the accuracy decreases to 78.13%. Next, we have incorporated the concept of 10-fold cross-validation technique. The program randomly divides the 192 observations into two groups. 173 observations are used for training and remaining 19 for validation purpose. From these 19 instances, one at a time is taken and corresponding accuracy is calculated. The average of these 19 accuracy results is given in table 4 and 6 for SVM and SMO respectively. As the accuracy values given in table 4 and 6 are less than those in table 3 and 5, it could be the scenario that proper division is not while segregating the dataset into training and validation. The 19 instances chosen for validation set come from one practical action, thus making a weaker pattern for that action, so wrong classification occurs. This in turn makes the average accuracy lower than the earlier ones, as this division of dataset is done automatically by the algorithm, so proper shuffling of observations is not present over there. Now the feature scope. The proposed work can be extended by applying electroencephalogram analysis in it. The use of EEG in finding the ability of the player of following the shortest path and measuring the actual path from the shortest path will eventually help us to detect the exact area and reason of player's falls. If it detects that there is a problem in occipital region of the brain, then it will mean that the player is visually weak. If there is problem in any lobe other than the occipital, then it can be depicted that there is problem in audio signal processing. By adding EEG, we will be able to measure mental judgment power, and that will contribute in cognitive rehabilitation also. Now the discussion part comes. It's a novel approach to motor rehabilitation using an interactive game with overall 100% accuracy of classification by SVM. The hybrid sensor architecture of Kinect sensor and accelerometer as data acquisition devices has been executed well, as they are efficient in extracting features, and PCA has been effective to reduce the feature dimension to the minimal. The paper can be summarized as the following points: robustness analysis, convenience, benefits, productivity, convergence, flexibility, feasibility, efficiency, computational time, and reliability also as well. So that's it for today. Thank you.